All right, so we've been talking about the declining population paradigm, which involves those deterministic processes that can cause large populations to become small. Those include harvest, habitat loss, pollution, invasive species. And we're going to have a chance now to implement some of these processes in our models, and specifically in Insight Maker. And we're going to limit this in this demonstration to just harvest and habitat loss processes. But as you can see, even implementing those processes get somewhat complicated. So this is going to be the model we are working with. And let's just get right to it. So let's move over to Insight Maker. So what I would say is just click on this link, and that's going to pull up this Insight Maker model. I'm not asking you to build this model from scratch because that would be a lot to do. But please load the model and clone it. And you can pause the lecture if you'd like, and I will move over to Insight Maker and give you a second to catch up. And here is our model. We can, first of all, let's just simulate from this model, and oops, there we go. Let's simulate. And it's, it looks complicated, but it's basically just our old friend, the logistic growth model, with a little stochasticity involved as well. So we added stochastic processes, births. Of course, we're drawing the total births from a Poisson distribution, like we've been doing. And for deaths, we're drawing the total number of deaths from a binomial distribution, as we have been doing. And so that's really the only difference here. Essentially, this is our logistic growth model with a density dependence on fecundity and a density dependence on mortality. And when we start well under carrying capacity, the model exhibits kind of an S-shaped curve up to carrying capacity, and it just bounces around a little bit because of demographic stochasticity. In addition, this model includes a couple processes that are deterministic threats to this population, including harvest, which we've done before. That's just a flow directly out of the population stock. And we have two different types of harvest. One is a proportional harvest, so every year a certain proportion of the population is harvested. Or absolute harvest, which is a certain number of individuals are removed from the population every year, regardless of how many are in the population right now. And that can mimic something like a harvest quota or something like that, where you can harvest up to a certain amount and then no more. So two types of harvest. And as well, we have this carrying capacity over here, and we have habitat loss. And we're modeling habitat loss as a loss in carrying capacity. And we can think of carrying capacity as just the total number of individuals that can be supported in this habitat. And habitat loss is just a reduction in the total number of individuals that can be supported in this area. And we can have, again, two different types of habitat loss. One, every year we remove a proportion of the total carrying capacity for the population. Or we can remove the capacity every year. We can remove a certain number of individuals that can be supported from this habitat. So say we start off with a carrying capacity of 100, and then every year we lose, this habitat loses the ability to support 2 individuals. So the next year the carrying capacity is 98. The next year it's 96. So 2 types of harvest and 2 types of habitat loss. Note as well that carrying capacity is linked to the population dynamics, births and deaths, by way of these density dependence terms. So we have this density dependence on fecundity, which we represented as, I think, the term A in our logistic growth model, and this density dependence on mortality, which we, I think, represented as the term C in our models. But really, those terms together help to define carrying capacity, and we can actually model carrying capacity explicitly and we can just link these density dependence terms to carrying capacity. And so what we see is that as the carrying capacity goes down, the density dependence terms actually become larger. And that should make some sense, because as carrying capacity is reduced, you will feel more crowding. If you have 100 individuals and the carrying capacity is 200, you're doing pretty well. You're probably pretty healthy and you're able to access a lot of resources. What if the carrying capacity is halved? Now carrying capacity is 100, your population's at carrying capacity, and you feel really crowded. So that strength of density dependence is really a function of carrying capacity. And so that's how we're modeling this. So hopefully this makes some sense. I know it looks complicated, but it should make some sense given what we've learned so far. All right, so now let's start playing around with deterministic processes. And let's start with harvest. We've done a little bit of exploring harvest models, but we can do a little more here. And let's first of all just make sure that your simulation length is running for 50 years. And simulation time step should be 1. So we looking good here. And the first step is to increase our initial abundance. So let's move our initial abundance to 1/2 of carrying capacity, which I think is 200. Let's just check that. Yeah. So the carrying capacity is 400, and so we can set our initial population to 200, and if we run it, we see that it quickly jumps up to carrying capacity. And let's set our harvest as a fractional harvest. So 10% of our population will be harvested every year under this model. So 10%, we can just move the mean fraction harvested to 0.1. That should be a period, 0.1. And we can see what that looks like. All right. And now let's actually add some stochasticity on the harvest process. We may not be able to predict how many will be harvested or what fraction of the population will be harvested each year. And so we can actually put a standard deviation on that. And we're modeling harvest here is actually, if you look at this, it's a normal distribution with a mean fraction harvested and a standard deviation on the fraction harvested. So we are asked now to, so say we have a population or a harvest rate that varies from approximately 5% of the population each year to 15% of the population each year. Now, how are we going to define this normal distribution then? We know the mean should be 10% or 0.1, so that's good, but now we know that the harvest rate varies between 5% and 15%, and we want to translate that into a normal distribution. So what should we put as our standard deviation? So that is the first question that we are going to look at, and we can do this together as a demo. So do you think, just take an initial guess though, do you think the answer is 0.05 or 5%? So one standard deviation from 0.1 is then going to be 0.15, and one standard deviation below 0.1 is going to be 0.5. And so that is going to maybe vary between 5 and 15%. But it might be worth just taking a quick look at the normal distribution using a whiteboard here. And let's see how successful I am at using this whiteboard. Okay, here we go. So we're going to draw, oops, that's erase. That's needs to be on a pen here. So there we go. And there we go. Okay. So here we have the x-axis. We're going to put a mean. Normal distribution is defined by a mean and a variance. And so let me see how well I can draw this normal distribution here. Let's do... All right, it's not great, but hopefully this illustrates the point here. And so what we know so far is that the mean is equal to 0.1. So that's 0.1. And we want this thing to vary. We know kind of the minimum. Let's see, the minimum equals 0.05, and the maximum is equal to 0.15. And so we can kind of think of this as the maximum here, 0.15, and this as the minimum, 0.05. And when we look at a normal distribution, we should think of one standard deviation as being kind of like right here. That's one standard deviation, and this is more like two standard deviations, because here we go. And here's one standard deviation, and here's two standard deviations. We can write it out as this is plus 2 standard deviations from the mean, and this is minus 2 standard deviations. And it's just the way the normal distribution works out. Now, standard deviation is like most of the values, about 66% or something, fall within one standard deviation, but around 95% of the random numbers you get out of this distribution should fall within 2 standard deviations. So if you're given a minimum and a maximum, you should think of that as kind of representing the area within 2 standard deviations of the mean. Now, if 2 standard deviations of the mean is 5%, so this is 0.1, this is 0.15, one standard deviation should be half of 0.05, or 0.025, equals 0.025. That would give us this distribution that has a minimum of 0.05 and a maximum of 0.15. And so when we can go back now and we can specify this standard deviation of 2.5% or 0.025, and we should get a distribution that varies between approximately 0.05 and 0.15. So that's just an aside about probability and statistics, but it's useful to know something about the normal distribution because it comes up so often in real systems. Real variables that we measure in the field are often normally distributed, so it's a very important distribution to know something about. All right, so let's go back to InsightMaker. And now instead of 0.05 here, we can move this and replace it with 0.025. And that's going to better answer our question. So we've now specified a population that has a stochastic harvest. And let's just simulate it now. There we go. All right, so we have a stochastic harvest model. And of course, if we really want to see what's going to happen here, we'd have to do sensitivity testing tool and run it a bunch of times and see what happens. And we see that we get a population that's fairly stable, it doesn't go extinct, and this deterministic threat is unlikely to cause a major issue for this population. It's just stabilizing at a little below carrying capacity, which is 400. So that's what's going on in this model. One question for you is, we've talked about stochasticity a lot recently, and we've just added a stochastic component to our harvest model. So we have the fraction of the population being harvested is a stochastic component. Now, is this demographic stochasticity or is it environmental stochasticity? Take a minute to think about that. What do you think? Is it luckiness or unluckiness at the level of the individual? Or is it more luckiness or unluckiness at the level of the population? If this year there is a really high harvest rate, that affects the whole population, right? And if this year there's a really low harvest rate, that's really good for the population, essentially. So is that demographic or environmental stochasticity? If you answered environmental stochasticity, you're right. It's kind of an interesting way to think about it, but really it's a type of environmental stochasticity that we're including in this model. So why doesn't this harvest lead to extinction? Well, it's fractional harvest, and we're just able to to find a new equilibrium, essentially, that we've kind of reduced the equilibrium state so that it's below what the carrying capacity would be otherwise. And we've seen this in a previous lab, but it's perfectly sustainable. So we're well above the maximum. Well, we're below the maximum sustainable yield rate, and we the population, even with all the stochasticity here, there's not much to worry about. The population's doing okay. All right, so let's look over at let's see what happens if you start making the harvest rate higher. What if you make it 20%? Still looks okay. What I'd like you to do is to pause the video and try this scenario. Try changing the harvest rate to 40%. So a 40% harvest rate, and I'd like you to change the standard deviation of harvest to 20%. So it's going to be a huge variation in the harvest rate. What happens? And there's a top hat question on this scenario. So try running the scenario. Harvest of 40% per year with a variation or standard deviation of 20%. And remember to use the sensitivity testing tool. And let's return now to this playground and Insight Maker for exploring the impacts of deterministic processes that can cause large populations to become small, like harvest and habitat loss. And we've already looked at the harvest process in some detail now. So let's move on to the habitat loss process. And just remember that we're modeling habitat loss as a decline in carrying capacity over time, either a certain fraction of carrying capacity lost each year, or a certain number of individuals, capable that the habitat is capable of supporting, is lost at a fixed rate per year. So, maybe a loss of 2 or 5 per year. And remember, carrying capacity is in units of individuals that can be supported by the habitat, sustainably. And so it could be 100 one year, then 98 the next year, and 96 the next year, in kind of a linear way. The harvest or the habitat loss is causing this linear change in carrying capacity. All right, so just make sure you remove any harvest process that's in your model. So make sure all these are set to 0, because we're going to focus now on habitat loss. So first, let's run a scenario where 10% of the habitat is lost every year. So this is the mean fractional habitat loss. Move that to 10%. Remember that 10% harvest rate didn't do that much to the population. The population was able to sustain itself fairly well through a 10% fractional harvest scenario. Let's look at a fractional habitat loss scenario of 10%. So make that change and hit the simulate button, and you see that this scenario doesn't look so good for our population. Let's look at what abundance is like over time, and you see it goes to 0 by year 50 in this case. Now it is stochastic, so probably every time it might look a little different. This time there's 1 left at year 50, but it's not looking good for this population. And of course we could run it many times with the sensitivity testing tool. I won't do that right now. But what I want you to just think about is this a realistic habitat loss? Would habitat loss look like this in real systems? Now, that's a tough question to answer, because habitat loss comes in so many different forms and shapes and sizes. There's really no one type of habitat loss. This probably is representative of some types of habitat loss, just as a more linear loss is also probably realistic in some cases. So we could change this to an absolute habitat loss of 1 per year and see what that looks like. And that could be a realistic type of habitat loss as well. And oftentimes of course, there'll be some stochasticity involved. So habitat loss, the amount of habitat might vary a little bit year to year. So this might even be a more realistic scenario. And many of you in your final projects will probably include some processes like this, or changes in habitat loss, changes in harvest. And sometimes these processes are difficult to predict, and it's good to add a stochastic component, a random number generator, to even these processes. All right. So we looked at 10% fractional habitat loss. It didn't look so good. That was not very good looking for the population. Here we go. Run it one more time. And that's what it looks like. So not so great. But if we change habitat loss by 1 per year, that looked okay. What if we change that to be a little bit more? We could change that to 5 per year. What happens there? All right, so that's still okay. So it's not great. Obviously, we've reduced the population quite substantially, but over 50 years, it's not terrible. And I think if we run the sensitivity testing tool, let's look at it, but I doubt there'll be any extinctions. Yeah, so the smallest it ever gets is around 135, but there's no extinctions here. All right. Let's start thinking about what if there's both habitat loss and harvest going on at the same time. This is called competing threats. It's actually something that's kind of a hot topic in conservation biology, is trying to study what happens when threats come together. Are they synergistic? That is, when you put them together, are they more than the sum of their parts? Do they have a bigger impact on the population than would be expected if you just look at one and look at the other and just add them together, for instance? Is the effect worse on the population than you would expect? Or is it better? Like maybe you put them together and there's really no difference between that scenario and a scenario with just one of those two threats. So maybe they're less impactful together than you would expect. So it's, again, a hot topic, and this is something that we can look at just using this simple modeling framework. So let's think about a scenario where we harvest 35 individuals per year. So we're going to have an absolute harvest of 35 individuals per year, and let's take this habitat loss away. So now there's just an absolute harvest of 35 per year. You can see, okay, that's sustainable. That looks pretty good. I mean, doesn't look great, but you have a population of around 260. It's not terrible. Now, let's return to that habitat loss, again, of 5 per year. And again, we remember that, it gets down to 150, but it's not going to go extinct. What I'd like to ask you to do is to combine those two scenarios. So take a scenario where you have absolute habitat loss of 5 individuals supported by the habitat per year, and add an absolute harvest of 35 individuals per year. Now see what happens. What happens in that scenario? And there's a top hat question that I'd like you to answer based on that. Now, just a few other points I'd like to make before ending this lecture, and that is, number one, this is, there's a lot more you can do with this scenario, so I'd encourage you to play around with this Insight Maker model and try different scenarios of habitat loss and harvest together, and see if you can find some interactions that are synergistic, that have a higher impact on the population than you'd expect, and others that have a lower impact on the population than you might expect. Again, just play around with it and see what you think. One interesting point here is that this type of model, I know it's simple, but it actually has some potential to answer some questions that are really kind of unknown and of interest in conservation. And one that comes to mind is looking at the overall impact of stochasticity in habitat loss and stochasticity in harvest. Now, this model is perfectly capable of looking at the impact on the population on a very simple kind of logistic growth model, but the impact of stochastic habitat loss versus stochastic harvest. Now, which of those two processes is more important to think about stochasticity? That's not a question that is widely understood or known. This type of model can help us look at that. So we're getting to the point in this class now where we're able to build models that can answer questions that are of real interest to the scientific and conservation communities. And that's kind of exciting. So take a minute again to explore this model and perhaps to answer some questions that really have not been addressed in the scientific literature. So that's where we are. Have fun with it, and I will see you next time.